ionization energy is defined as the energy required to remove one electron from an atom or ion in the gas phase. And that process is reflected in the reaction shown here, where we start with an atom in the gas phase, Xg, and we see that it loses an electron and gets converted to an ion, also in the gas phase. Since this is the loss of the first electron from the neutral atom, this process is called the first ionization energy. The trend in ionization energy in the periodic table is shown here, where we see that the ionization energy tends to increase as we go across a period or row in the periodic table, and it also increases as we go up a group in the periodic table. The trend in ionization energy is reflected in the graph shown here, where we have the first ionization energy plotted as a function of the atomic number. There are two notable exceptions. One occurs in group 2, and another one occurs in group 15. And those are significant because they represent a filled S subshell and a half-filled P subshell, respectively. And those two electron configurations are important because they tend to be particularly stable electron configurations. Here we see what we mean by half-filled subshell, where we have, in the NP3 configuration, we have one electron in each of the three p orbitals. There's also another trend in terms of ionization energy, and that's a diagonal trend, where we see that as we go across a diagonal from top left to bottom right, we see that the ionization energies are very similar. And this is due to the fact that the effective nuclear charge increases as we go across a period, but it decreases as we go down a group. And so those two effects somewhat cancel each other out. And this is an example of a diagonal trend. Here we look at successive ionization energies. As we might recall, the first ionization energy is defined as removing one electron from a neutral atom in the gas phase. This results in the formation of a +1 ion in the gas phase. The second ionization energy is defined as removing one electron from the +1 ion in the gas phase to produce the +2 ion in the gas phase. And similarly, the third ionization energy is defined as removing one electron from the +2 ion in the gas phase to produce the +3 ion in the gas phase. So, for a given element, the ionization energies increase as we move from the first to the second to the third ionization energies. And this occurs because removing an electron from an increasingly positive species is energetically unfavorable or difficult to do. However, you'll notice that in some cases there is a large increase in the ionization energy. And we can explain this by looking at the electron configuration for beryllium, which is 1s2, 2s2. So we can see here now that the electrons in the 2s atomic orbital are the valence electrons, or the outermost electrons, and these are the ones that normally participate in chemical bonding. So we can see that removing the first two valence electrons might be relatively easy. However, once we want to move the third electron, we are forced to start removing core electrons, which again is energetically unfavorable. And so we see here that the large increase in ionization energy, going from the second to the third ionization energy, is due to the fact that we are starting to remove core electrons. Okay? And so in this case, the third ionization energy for beryllium is much larger than the second ionization energy. Here we have the ionization energies for a variety of different elements in the periodic table. As you can see, in some cases we have a large jump or increase in the ionization energies. For example, going from the first to the second ionization energy for lithium, going from the second to the third ionization energy for beryllium, and going from the third to the fourth ionization energy for boron. As we mentioned previously, this large jump or increase in the ionization energy is due to the fact that we are starting to remove core electrons. Just to summarize, as the number of shells in an atom increase, the shielding of the electrons from the nucleus increases, and therefore the size of the atomic radii increases, and because of that, the first ionization energy decreases.